Hello friends, in this video we are going to study about regioselective and regiospecific reactions and also about stereoselective and stereospecific reactions. Let's begin with regioselective reactions. Let's take this olefin. Okay, 2-methyl-butene perform a Markovnikov addition. What will be the product? You will get chlorination here and you will get chlorination here, and this one is a major product. Okay, we get two regioisomers. Strictly saying, these two are called constitutional isomers. For convenience, let me call them as regioisomers because these isomers have the same molecular formula, whereas only in the region where the chlorine has attacked. Here it is at the secondary carbon, here it is at the tertiary carbon. So out of these two stereoisomers, one is forming as a major product. That means one is favored. Selectively, one regioisomer is forming in this reaction. So this reaction is called regioselective reaction. Selectively, one regioisomer forms. Okay, and is there any regiospecific reaction? Take up this one. 2-methyl-propene perform the same Markovnikov addition. You will be getting okay, this is the only product. You will get only this isomer. Though there is a possibility for other isomer, you won't get this isomer. Okay, you will get only this isomer selectively. Okay, so in that case, this reaction is called regioselective isomer. There is a possibility of two regioisomers, but only one isomer forms. That means selectivity is 100%. So in that case, this reaction becomes regiospecific. This one is regioselective. Selective because both are forming, one is major. So this is selective, this is specific. Okay, what is the reason? Look at the carbocations. Look at this here. The carbocation for this one is, this is a carbocation, a tertiary carbocation. A carbocation for this product is a primary carbocation. Okay, primary is very unstable than tertiary. So in that case, being very unstable, this primary carbocation doesn't form at all here. Only tertiary carbocation forms, precisely tertiary carbocation forms, which is a stable one. So giving only this product and making this reaction regiospecific. But in this case, if we consider the carbocation for this product, here it is a secondary carbocation. And in this case, you get a tertiary carbocation. Okay, out of these two, tertiary is more stable. However, secondary is also stable, but not as stable as tertiary. So two carbocations are possible. Out of this, the stable one is major, so it gives a major product. However, the secondary cation gives this product as a minor isomer. So because of the formation of these two carbocations, this becomes a regioselective reaction. But here, because of the formation of this only one carbocation, a stable carbocation, this reaction becomes regiospecific. You can find this example from Paula Bruce Organic Chemistry. Okay, now let's see the stereospecific and stereoselective reactions. Look at this. Let's consider this Bridget bicyclic alkene. Perform epoxidation MCPBA, metachloroperbenzoic acid. The product is the product is an epoxide, and there is another product this is also an epoxide, and first one is endo, this one is exoisomer, and this one is the major one. Exoepoxide is major. So actually there is a possibility for the formation of two stereoisomers, exoisomer, endoisomer. Out of that, exo is a stable one and it is forming as a major product. So here is a selectivity on exoisomer. There is a possibility for two stereoisomers, but one is selected. So this is a stereoselective reactions. And how about the stereospecific reaction? Look at this one. OTS. Perform an SN2 reaction, OAC, as a nucleophile. Your product is okay. So if you look at the RS nomenclature, 1, 2, 3. Here it is R, and here it is S. Okay, you know that SN2 reaction, the nucleophile approaches the carbon on the backside of the leaving group. Here, nucleophile, leaving group is the front side, nucleophile attacks on the backside, so you get the OAC on the backside, because SN2 reaction is known for Walden inversion. Since this product is since the starting material is a regioisomer, there is an inversion of configuration takes place. Okay, so if we go to the other stereochemistry, the complementary stereochemistry, OTS on the back side. So this configuration is yes. So if you perform the same reaction, you will get OAC. Now the leaving group is backside, so nucleophile comes at the front. So this is R. So look at these two examples. If we want S, you have to start with R starting material. If we want R configuration, you need to start with S. Okay. For S, start with R. For R, start with S. You can't get R from R. You can't get S from S. Okay. So that means what? The stereochemistry of the product is determined by the stereochemistry of the reactant. In the mechanistic pathway, the stereochemistry of the reactant dictates the stereochemistry of the product, and there is no choice. Okay. So this is stereospecific reaction. Specific reaction. But here there is a choice. In the mechanistic pathway, there is a provision to have a choice for the stereochemistry of the product. Even though the mechanism favors one stereochemistry, one stereoisomer, there is a choice for the other stereoisomer also. So in that case, it is stereoselective. So what you need to remember is the stereochemistry of the product is determined by the stereochemistry of the reactant. By seeing the stereochemistry of the product itself, you can predict the stereochemistry of the reactant. So in that case, you can call it a stereospecific reaction. And there is one more example. Let's begin with this trans-stilbene. Do the epoxidation with the NCPBA. You will get trans epoxide. You started with trans, you ended up with trans epoxide. If you start with cis stilbene, you will get cis epoxide. Okay, trans to trans, cis from cis. Okay, so the stereochemistry of the product is determined by the stereochemistry of the reactant. You can't get trans product from the cis olefin. Okay, you can't get cis product from the trans olefin. If you want trans, you should go for trans. If you want cis, you need to go for cis starting material. Okay, so stereochemistry of the product is determined by the stereochemistry of the product, and there is no choice. This is stereospecific reaction. Let's see one more example. We are familiar with this right from our BSc classes. Let's take this stilphene, cis-olefine. Do the bromination in carbon tetrachloride. You get a cyclic bromonium ion. And next step is the bromine. Bromide attacks from here or here. If it attacks this carbon, let me say, if it attacks this carbon, Br, pH, H, again, pH, H. If the attack takes place at this carbon, Br, pH, H. In the same way, Br, pH, H. Okay. If we convert these two, both are staggered conformation. If you convert them into eclipse conformation, you will get a conformation which I write in Fischer projection. So I can write it as Br, pH, H. In the same way here, if we write Br, pH, H. What is the relation between these two? They both are mirror images, racemic mixture. Okay, they both are enantiomers. Okay, they both are enantiomers. In the same way, same sequence of transformation, if you try in this, in the trans product, in the trans olefine, you'll be getting in the same way what are these two? These two are mirror images, but they are meso compounds. So if you start with cis olefine, you end up with racemic mixture, but not meso. If you start with trans olefine, you end up with a meso, not racemic mixture. So the stereochemistry of the product, if we want meso, you need to start with trans olefine, not with cis olefine. If we want racemic mixture, you need to start with cis olefine and not trans olefine. So stereochemistry of the product or products, okay, determined by the stereochemistry of the reactants. Okay, so this is another example of stereo-specific reactions. I hope you understood. We'll meet in the next video with some other examples. Okay, thank you very much. Wish you all the best.